Let us now welcome Professor Wilczek with our warmest applause. Welcome.
Thank you. Thank you. It's inspiring to see so many bright young faces.
You can use your earphone.
Yes. And I'm very happy to be giving this lecture at my new home here at SJTU and in Shanghai. So my subject today is origins of mass. The first question you should ask is, what the heck does that mean? Has mass an origin? It's by no means obvious that it makes sense to ask for the origin of mass. In fact, the traditional concept of mass, the concept that was extremely fruitful in the early days of physics, that was introduced by Sir Isaac Newton, indicated that mass had no origin. Newton referred to mass as quantity of matter. So he thought of mass as an intrinsic property of matter that couldn't be taken away. No mass, no matter. This was so basic in his thinking that when he enunciated the famous laws of motion, he didn't even state the most basic law of all, which makes the whole system work. I call it the zeroth law of motion. This is the conservation of mass. It says that every body, every piece of matter has some mass, and if you have a whole bunch of bodies and they stick together, or you regard them as a system, the total mass of the system is just the mass of all the constituent particles, and that total mass stays constant. If that were true, there's no deeper level of explanation. The mass is always the same quantity. It never changes. It doesn't make sense to ask about its origin. It's just something that matter has. This concept of mass served physics very well for over 2 centuries. It was also the foundation of chemistry. Lavoisier, in the experiments that founded chemistry, looked for missing mass in the process of combustion, and in that way discovered the existence of oxygen taken from the air. But over the 20th century, our concept of mass has changed radically. There were, in fact, I would say 4 separate revolutions in our concept of mass. In special relativity, we learned that energy is more basic than mass. So mass is not a primary quality of matter that doesn't change in time. In quantum chromodynamics, or QCD, we learn that most of our mass, most of the mass of our bodies, in fact, is pure energy. We are mostly made out of particles that have 0 mass or almost 0 mass. The vast bulk of our own mass, of our own bodies, comes from pure energy. In the theory of other particles' masses, including the electron's mass, we learn that some important particle masses, not most of the mass of our body, but some very important pieces, comes from the drag of a cosmic medium. And at the frontiers of knowledge today, in cosmology, we learn that most of the mass in the universe is strange and/or mysterious. So in the rest of these lectures, rest of this lecture, I'll say more about each of these 4 things, one by one. So let me first explain the concept of mass as it's changed in the special theory of relativity and quantum field theory. Now, I hope you won't be too scared by quantum field theory. It takes years to learn properly, but I will not use very much, and I'll tell you exactly, and I won't mathematically derive anything. I will just use some very basic results of quantum field theory. You'll find them very simple to understand, and don't panic. So, perhaps the most famous formula in all of physics is E equals mc squared. And it's not exactly false, but it's kind of misleading. It's a very special statement about the relationship of mass and energy. If you took it literally as E actually equals to mc squared, it would say that the energy is the mass times the speed of light squared, and mass would be essentially the same thing as energy, just multiplied by a constant. But that's not really what the special theory of relativity says. The more accurate version is that associated with any particle, there's its mass, m, little m, and when it's moving, it has moving at some velocity v, it has an energy given by the formula you see there. The energy is the mass times the speed of light squared divided by the square root of 1 minus the velocity squared over the speed of light squared. When the velocity is 0, this becomes E equals mc squared, but that's only a special case. And when you have a bunch of particles together, the total energy is the sum of the energies. The masses do not add, it's the energies that add, and it's also the energy of the whole thing that's constant. So mass now is not the most important quantity. Energy is the most important quantity. Mass is not conserved. The mass of the whole, for instance, 2 protons in that picture, in that movie you showed, starts with just 2 protons, and out come zillions of particles. If you added the mass of all those particles at the end, it would be much more than the mass of 2 protons. So the mass is not conserved. Mass is created in such a reaction. But energy is conserved. These are the facts from quantum field theory that you have to realize to understand the deeper discussion that follows. That is that fundamental particles come in units, quanta, of a few kinds. Most notably, the quanta that we're made out of are photons, electrons, quarks, and gluons. The quarks come in 2 types. In a complete accounting of what's in the world, there are many other kinds of quanta, a couple of dozen in all that are known, including neutrinos, Higgs particles, W and Z bosons. But these are the ones that are reasonably stable and out of which we are made. And each of these quanta, each of these fundamental building blocks, has its own characteristic mass. So any 2 photons have an equal value of this mass, little m. Any 2 electrons have the same value, m sub e, and so forth. That's what you need to know about quantum field theory. Particles can also have 0 mass. This was something that wouldn't make sense in Newtonian mechanics. Particles with 0 mass wouldn't know how to move. F equals ma. They'd go crazy. You have to divide by 0 to figure out how to move. And also in the theory of relativity and in modern physics, they're very special. They can still have non-zero energy, but they must always move at the speed of light, and they obey especially beautiful equations. You'll have to take my word for that, but ask any physicist. They'll tell you. In fact, two of the most famous systems of equations in physics are the Maxwell equations for electrodynamics, which are the equations for massless photons, the particles of light, and the Yang-Mills equations, which are the brainchildren of these two gentlemen, C.N. Yang and Robert Mills, which is a generalization of the Maxwell's equations, which governs the behavior of gluons and which are also massless particles. In fact, I jumped the gun a little bit. I wanted to say that not only are these particles with zero mass special, but nature, and not only are their equations beautiful, but nature likes them too. Photons and gluons have zero mass. Okay, so with that background from the foundations of 20th century physics, now we can discuss the origin of your mass. It actually follows from this version of Einstein's law, E equal to mc squared for a particle at rest. I like to call this Einstein's first law. Einstein's second law is E equals mc squared. There's also a third law, which is c squared equals E divided by m. I call this the first law because this is the one that you'll actually find in Einstein's original paper. In the original paper where Einstein discussed the relationship between mass and energy in the theory of relativity, this is the equation you'll find, not E equals mc squared. And in fact, the title of that paper is, Does the Mass of a Body Depend on its Energy Content? So right from the beginning, Einstein was thinking of the idea that mass might come from energy stored within the particle. So, some basic facts about you. The mass of atoms is concentrated in their nuclei, these small, dense objects at the middle of atoms. Atomic nuclei are composed, accurately enough for our purpose, of protons and neutrons. But protons and neutrons are complicated objects. This is a snapshot of a proton. It's kind of an artist's impression, actually. But you can take snapshots of a proton using high-energy accelerators and some very clever image processing. And if you do that, you do find that the proton is very complicated. It contains lots of gluons, those are the springs here, and quarks and antiquarks, which are the little balls. Quarks and gluons are the simpler, more fundamental particles from which protons and neutrons are made. Whereas the equations that describe the behavior of protons and neutrons are very complicated, the equations that describe the behavior of quarks and gluons are very simple. They're basically the Yang-Mills equations that I alluded to before. And the theory based on those equations is called quantum chromodynamics, or QCD, and it's been tested very rigorously and very directly in experiments that see quarks and gluons. Now, if you look at a textbook or even read Wikipedia, you may read that quarks and gluons can't exist as free particles. They're always found only inside other particles like protons. But that's not quite true anymore, or that's an obsolete point of view, because I'll show you a picture where you actually can see a quark and an antiquark. What this picture is you have electron and anti-electron colliding at very, very high energy. So coming down this red tube in the middle, meeting and colliding in the middle, and when they collide, their energy associated with their very rapid motion is turned into other kinds of particles. Mass is definitely not conserved, as I said before. But what happens, according to the theory, is often you will produce a quark and an antiquark moving rapidly in opposite directions. So you start with an electron and an anti-electron. With high energy, it becomes a quark and an antiquark with very high energy. Now, quarks and antiquarks can't exist as isolated particles, but according to the formulas of QCD and the phenomenon of asymptotic freedom, what does happen is the quark becomes a whole bunch of things like protons and antiprotons and mesons of various kind, moving rapidly in the same direction. So a quark becomes a so-called jet, which is several particles moving rapidly in the same direction as the original quark, and the energy and the momentum of those particles add up to the original quark. And in the opposite direction, you have the original antiquark materializing into its jet, which is also carrying the same total energy and total momentum as the original antiquark. So if you squint and pretend that these jets are single particles and just count their energy and momentum, you're seeing the quark and the antiquark. And the equations that tell you how the quarks and antiquarks behave can be applied to those kind of effective particles. And in that way, we get to test the theory. Sometimes, in these collisions, you have three jets coming out. And in that kind of event, what's happened is you produced a quark and an antiquark, and the quark has radiated a gluon. Or maybe the antiquark has radiated a gluon. Somebody's radiated a gluon. And then the gluon makes its own jet. And because you have this very direct window into the underlying basic particles, you can check the equations in great detail. And they're correct. That's how I got my Nobel Prize. Yeah, okay. Thank you. Now, we can also make better pictures of the interior of protons if we calculate, as opposed to doing experiments and counting on artists to make an impression of the experiments. We can actually calculate using the equations. Now that we know that they're correct, we can calculate using the resources of modern powerful computing what the behavior of all these gluons is. And this is what you would see inside a proton if your eyes could work much, much faster and had much, much better spatial resolution than they in fact have. If you could see distances as small as 10 to the minus 14th centimeters and resolve events that happen as fast as 10 to the minus 24th seconds, this is what you'd see. You'd see that in empty space, there are fluctuations in the amount of energy in gluon fields, and this is responsible for holding protons together and for a lot of their mass. So let's return from this basic knowledge of how protons are made from quarks and gluons have a compelling theoretical description to the question of the origin of mass. Well, about 120 years ago, Hendrik Lorentz, a great Dutch physicist, famous for Lorentz transformations, among many other things, proposed a visionary theory of the origin of the electron's mass. This was perhaps the first theoretical attempt to really make an account of the origin of mass. It was even before the special theory of relativity. So when I say visionary, it was wrong. It was ahead of its time, but very suggestive, and in fact, partially inspired the theory of relativity. According to Lorentz's idea, if you have a charged particle like an electron, it has electric fields, and if it moves, it also has magnetic fields. Those electric and magnetic fields have energy, and they may resist motion. It may slow things down if you try to move electric and magnetic fields around. And in fact, Lorentz attempted to calculate this effect. According to Lorentz's idea, it's that inertia, that reluctance of electric fields and magnetic fields to move, which slows down electrons and is responsible for the effect we call mass. So you could start with a massless concentration of charge, just calculate the motion of the fields, and produce mass. Well, that never really worked in detail, but it's exactly what happens in quantum chromodynamics, or QCD. About 95% of the mass of protons and neutrons, which is the overwhelming percentage of our own mass, of humans, and of everyday matter in general, arises as the pure energy of quarks and gluons moving around. So they move around inside this proton. That gives them energy, according to the formulas of special relativity. You divide that energy by c squared, and you get the mass of the proton. And this is not just talk. You can actually calculate, using powerful computers and using the precise equations of the theory, the masses of many different particles, many different ways of arranging quarks and gluons that nature can use, and this is what you find. This is a discipline called lattice gauge theory, which allows you to solve the equations of quantum chromodynamics and find what sorts of concentrations of energy of quarks and gluons have a reasonably long lifetime, so that they are particles. And you can compare those to the particles that are found in the laboratory, and you find an extraordinarily good agreement. Okay, so there are three inputs to this calculation to fix the theory, but then there's no more room for maneuver. The equations are completely definite, and you have to calculate, and it's either wrong or a great triumph of physics, and it turns out to be a great triumph. Now, among these particles, one of them, N, stands for nucleon. Those are the protons and neutrons. So this calculation, which starts from strictly massless gluons and almost massless up and down quarks, accounts for the origin of our mass. So if you're having trouble with your weight, you think you're too fat and are having a diet, you weigh too much, that's the problem. Now I'd like to discuss a second origin of mass, mass from drag. T.D. Lee, our Shanghai hero and the name attached to our new institute, Xian Yang, again, and Madame C.S. Wu taught us in 1956 and 1957 that there is a fundamental distinction between left and right. This is what Li and Yang looked like at the time. If they were sitting in this audience, they wouldn't look out of place. And this is what Madame Wu looked like at the time with her equipment. And this is the crucial experiment that she did, which shows the distinction between left and right in fundamental processes. So what it is you have the decays of cobalt-60 nuclei here. You put them in a magnetic field. Cobalt nuclei have a spin, and the magnetic field aligns their spin. And then you find that the direction in which electrons are emitted when cobalt nuclei are decay is preferentially in the direction against the spin. That's the phenomenon. Why does that show that right and left are different? Well, let's think about it. If we have a particle that's spinning, okay, we have some axis, and it's rotating around the axis. Okay? If you change left to right, reflect the thing in the mirror, reflect everything in the mirror, you'll change left to right, okay? And look what happened. The direction of spin has changed. Okay? To match the direction of the left-handed spin, I have to turn over like this. So, if you have this experiment and look at it in a mirror, it won't look the same because the spin direction will have changed, but the electron's motion will not have changed. So there's a fundamental distinction in the behavior between the actual experiment and its reflection in a mirror. There's a difference between left and right. To have different behavior for the left and right-handed versions of a particle, that particle must have zero mass. Why is that? Well, if a particle moves at less than the speed of light, first I should say, what do I mean by a left-handed particle and a right-handed particle? When I have a particle that's moving, okay, I have both and spinning, then I have both a direction of motion and a direction of spin. If a particle is spinning and moving so that the spin and motion match the configuration of a right hand, I call that a right-handed particle. If it matches the configuration of a left hand, which is the opposite, I call it a left-handed particle. Now, the phenomenon that Madame Wu observed and was generalized in many other experiments is that the electrons, another phenomenon that occurs, it wasn't originally what she observed, but closely related, is that the electrons that are emitted in weak processes are predominantly left-handed. So left-handed and right-handed electrons have very different behavior. One kind is produced in the decays, the other kind isn't. But to have a distinction between left and right-handed particles, those particles had better be moving at the speed of light. Because if they're moving at less than the speed of light, we can catch up to them, go past them, and if we go past them, their apparent direction of motion is different, although the spin stays the same. So if you move rapidly past a right-handed particle, it becomes left-handed. If there's going to be a fundamental distinction between left and right-handed particles, it better be impossible to catch up to those particles, which means they have zero mass. They're moving at the speed of light. But electrons do not have zero mass. So that was a huge problem. A deep problem brought about by the discoveries of Li and Yang and Madame Wu. The resolution came only many years later. It's by something called the Higgs mechanism. It's a bold idea. It says that, yes, fundamentally, electrons have zero mass. However, They're propagating through space, and space is not empty. Space is filled with some material that changes their properties, that slows them down, a kind of cosmic molasses. Maybe that's an unfamiliar word, but it's a thick syrup that slows things down. Imagine there were a distant planet where intelligent fish evolved. They might think they would eventually develop physics. When they first developed physics, they would have complicated laws of motion because the way things move inside water is very complicated. But eventually, some genius in physics, some genius fish, would figure out that they could get a simpler description of nature, a better description. This fish Newton would realize that you could get simpler laws of motion if you imagine you could take away the water and study things in an emptier environment. So we're like that. We're like those fish. We can get simpler equations, a simpler description of the basic physics. We can make a fundamental distinction between left and right-handed particles if we imagine that we live in a cosmic ocean that slows down the electrons. Now, in the 1960s and 70s, when these ideas were first being explored, physicists quickly realized that no known particle, no known field, not the electromagnetic field, not the photon, not gluons, not quarks, none of those things could construct the medium that would have the required properties to do this job of slowing down electrons. So they postulated a new one. And it got called the Higgs field, after one of the physicists who worked on this problem. It's a wild idea that the universe, and it also sounds like a desperate idea, that the universe is filled with some material so that our equations can be more beautiful. Fortunately, it has observable consequences. The minimal units or quanta of any field appear as particles. So, for example, photons are the quanta of light. They are particles that represent the minimal units of light. Gravitons are the quanta of gravity. Gluons are the quanta of nuclear force fields. If we have this space-filling medium, there has to be some fundamental unit. This is again quantum field theory. There must be some fundamental unit, some quanta of that field. The quanta of the Higgs field is called, without much imagination, the Higgs particle. Since we knew what the Higgs particle had to do if it was going to solve our problems with electrons and other particles, to give them mass, to produce the drag which would look like mass to them, for them, many of the properties of the Higgs particles could be predicted in advance of their observation. We'd seen the field, so we could figure out what the little bits of it, the quanta, would be, and design experiments to look for them. The experiments are not easy, but they're convincing. I won't attempt to convey the details of this, but just to say that the basic process by which the Higgs particle was discovered was inside of protons. As I told you, there are gluons. You shoot protons moving very, very rapidly in opposite directions at one another. This was done at the LHC collider at CERN near Geneva. And theoretically, you can calculate that two gluons can come together, meet a quantum fluctuations quantum fluctuation where you go to heavy particles, top quarks and anti-top quarks. Ordinary matter has very, very feeble couplings because the mass of electrons, quarks, and gluons is very small. So no direct coupling to the Higgs particle, but one of my proudest discoveries, actually, although it's very simple, is that gluons can communicate through to the Higgs particle effectively, efficiently, through quantum fluctuations to heavier particles. And then the Higgs particle, in a very, very tiny fraction of a second, decays back by a similar mechanism into photons, and photons are particles we know a lot about. We're familiar with them for a long time, and we can observe them. So in this way, even though the Higgs particle lives only a very short time, it produces photons that are very characteristic, and you can look for them. And here is the actual observation that represented the discovery of the Higgs particle. So when you studied at the accelerator pairs of photons, there are many, many processes that produce pairs of photons, but one of them is a process in which a particle, the Higgs particle of a definite mass, decays into two photons. The energy of those two photons added together must equal mc squared of the original Higgs particle, because energy is conserved. So the energy was mc squared plus a correction for motion if it's moving, and the photon's energy has to add up to that with a correction if they're moving also. So you should find, if the Higgs particle exists and you organize the plot of events properly, a contribution from the Higgs particle, if it exists, and that little bump, that tiny enhancement over the background of photons produced by other processes, was the discovery of the Higgs particle. A great triumph of theoretical reasoning and our understanding of the origin of the electron's mass. Now let me turn from those stories of triumph to the frontier of knowledge today, where we are still struggling. This, in fact, is most of the mass of the universe, the mysterious dark sector. It might be better to refer to the cosmological dark matter problem as the excess acceleration problem. That's what's actually observed. If we could observe the matter, it wouldn't be dark. It would be something we could study and figure out its properties. And I wouldn't be talking about the dark matter problem. I'd be talking about the particle. I don't know what particle. This doesn't have a name. The Taiji particle, the axion, this WIMP, some particle, but it wouldn't be called the dark matter. We'd know what it is. What actually is observed is not a particle or any kind of matter or any kind of interaction of light with matter or any kind of cosmic ray emitted by matter. It's nothing, nothing except that things are moving in a way that they shouldn't be moving. That is, that there seems to be more gravity observed in a whole variety of circumstances than there is matter to supply it. So we think we have very good theories of how gravity works, thanks to Mr. Newton and Mr. Einstein. And we can figure out what the gravity that causes motions of galaxies or planets should be. And things don't quite move that way. There seems to be more matter than than is observed. This excess acceleration, this faster motion, first showed up in analysis of the motions of galaxies within the Coma cluster of galaxies, but by now there are many indications of different kinds. The phenomena are broadly consistent with what's called the cold dark matter hypothesis. That is, that there's a new kind of particle, or perhaps more than one new kind of particle, that interacts very, very weakly with ordinary matter. The main interaction is through gravity, but we're also working to find other interactions so that we get a much better, more concrete idea of what this new matter, what this new particle or particles are. Let me briefly indicate a couple of the indications that are especially easy to explain and make nice pictures. So one phenomenon is this. So I mentioned in clusters of galaxies you have excess acceleration. Also within individual galaxies, if you can look at how fast stars are rotating around the center or moving radially, they're different kinds of motion. And you can compare to what what the motion would be due to the gravity of the kind of matter you see. The things like stars, gas clouds, all the kinds of matter that you can see with telescopes, radio telescopes, any kind of astronomical observation that we know how to make today. And what you find is that if you add up the motion of caused by the ordinary matter, you would get this curve, the so-called disk model. That's what the visible matter would predict would be the velocity of stars as they get further and further away from the center. Okay, the velocity would fall because the gravity gets weaker. However, what's actually observed is that the velocities level off and stay constant. If you ascribe this excess acceleration, this unexpected faster motion to unseen matter, then the kind of matter you infer, the distribution of matter you infer, this so-called dark matter, which doesn't look like this at all. Let me emphasize, you don't see anything. So it doesn't look, this is a fake picture, but it pictures not anything we see, but the theoretical calculation of how much mass there should be. The dark matter is distributed in a very, very broad diffuse halo that extends way, way beyond most of the visible matter. Another phenomenon that arises in the general theory of relativity and has been tested in many experiments now is that matter can bend the path of light. Light is also subject to gravitational fields. And if, therefore, you look at a very, very distant galaxy here, and that the light from that galaxy to get to us has to pass through a region where there's lots of matter, the path of the light can be bent. And as a result, there may be several ways that the light can reach us, in which case we'll see several copies of the object. Distorted, but we'll see several copies, and in general we'll see a distorted looking image of things behind lots of matter. And if you look out at the sky, in some directions you do in fact find very distorted images. So this is just one galaxy, but imaged 5 times, or maybe, I don't know, a lot of times. And you see this one is like become almost a ring of around. And this is due, theoretically, to the fact that the light from these objects has gone through, like a lens, a gravitational lens caused by matter in between the galaxy, the object you're seeing, and us. Like looking through the bottom of a glass soda bottle. And if you calculate how much mass is required to produce the observed amount of bending, again, you find, as in the case of the Coma cluster, as in the case of galaxies, so clusters of galaxies, here also you find that you need much more matter so-called dark matter much more mass than can be accounted for in terms of the objects that we know how to observe. So there are several different lines of evidence, all consistent with each other broadly. And the summary can be given in this little pie chart that ordinary matter, the kind of matter that you and I are made out of, the kinds that you'll study in chemistry and biology and engineering classes, the kind that's made out of electrons and photons and quarks and gluons, provides about 4.6% of the mass of the universe. This dark matter that clusters around galaxies and is seen in many other circumstances accounts for about 24% of the mass of the universe. That's called the dark matter. There's another contribution, which actually is the biggest of all, which I haven't even mentioned, the dark energy. And the dark energy is basically the energy, the density of mass itself, of space itself. A great discovery of recent years. Oh, sorry. A great discovery of recent years is that space itself has a tiny but non-zero entropy, non-zero density. And if you add it up in the whole universe, you know, most of the universe is empty of ordinary matter, but this little density adds up and adds up and adds up. Most of the universe is even empty of dark matter, but this stuff adds up and adds up and adds up. And although its density here in this room is very tiny and negligible, added up over the whole universe, it produces most of the mass. The dark matter is what I've been talking about, this stuff that clumps, bends light, holds galaxies together, and holds the coma cluster together, and so forth. Now, the fact that space itself has a density is very interesting, but we don't really know what to do about it, except admire it. So I won't say anything more about that. Dark matter, however, looks like it's some kind of particle, and the question is, what particle is it? And how else can we observe it? So this sets an agenda for research that's very, very exciting and very much in process these days. Physicists have promising ideas for what that dark matter might be, and the hunt is on. I hope in a few years, as a result of activity at the T.D. Lee Center and elsewhere, we'll be able to report exactly what this dark matter is, but all I can do now is show you a couple of the ways that people are looking for some of the more promising candidates. This is a beautiful countryside in Sichuan, where there's a mountain, and in that mountain, a tunnel has been drilled sideways. How long is it? 4.5 kilometers? 17 kilometers into the side of a mountain, so that you're under the top of the mountain, and that protects you from cosmic rays and things that would complicate the observation of very rare events associated with dark matter. But inside that mountain, there are experiments, and a prominent one is the Panda X module that's coming out of the T.D. Lee Institute. And this, in fact, has the world's record for most sensitivity to very interesting kinds of dark matter, the so-called weakly interacting massive particles, or WIMPs, that have a very good theoretical motivation. Unfortunately, so far, the results are negative, but bigger and better detectors will be built inside that mountain, and the hunt is on. Another idea is a particle called axions, very different, with different motivations. It doesn't contradict the WIMPs, but could be another contribution. Personally, it's my favorite. I named it, and I have a lot of fondness for it. Axions would have to be detected in a very different way, with a very different kind of antenna. The basic process is that in the presence of a magnetic field, axions once in a while will turn into photons, and photons we know how to observe. We use a big eyeball like that. Not really, but we know how to deal with photons. So if you can convert, if axions exist, we know that what their interaction should be like. They can convert into photons, and you can search for the photons. So this is another kind of experiment that's being done. You need very, very sensitive detectors. You need to do all kinds of tricks to make this tiny effect observable. But if axions exist and are out there as the dark matter, they should be detected in the next few years. Oh, what am I doing? Another interesting way to look for axions is to look around black holes. Axions would form, uniquely among particles, would form atmospheres around black holes. And now that people are able to study properties of black holes through sensitive astronomical observations, very accurate images, and also through gravitational waves that are emitted when black holes collide, we'll be able to figure out if black holes in fact are surrounded by atmospheres. So stay tuned. I hope in a few years, certainly by the time you're my age, we'll know. So let me summarize. Mass no longer represents rock bottom. In Newtonian physics, it did. It really didn't make sense. It was not a fruitful question to ask about the origin of mass. Mass just was there. It doesn't change. Nothing you can do about it. But no longer is that true. Now we can go deeper. We can discuss in an illuminating way the origins of mass. And we found at least 2 beautiful stories and another one under development. One is that most of our mass is pure energy. That makes me feel good. Some crucial mass, especially the mass of the electron, arises from the drag of a cosmic medium. But most of the mass in the universe still remains mysterious, remains to be accounted for. So thank you.